In an industry where costs soar and progress crawls, SpaceX is betting everything on a single, world-shifting gamble. Starship is a rocket so massive and ambitious that if it works, it could reduce space launch prices from thousands of dollars to mere tens of dollars per kilogram. But the nuclear option that could win the new space race depends on unproven breakthroughs, like catching giant boosters and fueling ships in orbit. What if this machine actually changes everything, or fails spectacularly in the attempt? Towering 120 meters above the launch pad, Starship stands as the largest and most powerful rocket ever constructed. Its lower stage, the Super Heavy booster, relies on a dense cluster of 33 Raptor engines, each burning methane and liquid oxygen with a full-flow staged combustion cycle. This engine design delivers not only immense thrust, but also high efficiency, allowing the booster to generate nearly 17 million pounds of force at liftoff. Clustering so many engines is a bold engineering move, providing built-in redundancy. So if one or two engines fail, the others compensate, ensuring the booster can still complete its mission. Above the booster sits the Starship upper stage, designed for both orbital insertion and deep space operations. This stage is fully reusable, equipped with its own set of Raptor engines and protected by thousands of hexagonal ceramic tiles that shield it during the fiery return through Earth's atmosphere. Both stages are built for rapid turnaround, aiming for refurbishment cycles measured in days, not months. Instead of ocean splashdowns, the Super Heavy returns to the launch site, where mechanical arms dubbed Chopsticks catch the booster as it descends, readying it for another flight with minimal downtime. Every aspect of Starship's architecture is shaped by the goal of slashing operational costs. Reusability isn't an afterthought, it's the foundation. The vehicle's immense size allows it to carry over 100 metric tons to low Earth orbit in reusable mode, or more than 250 tons if flown expendably. This leap in scale and efficiency sets the stage for a new era in spaceflight, where high-frequency launches and rapid reusability are engineered into the system from the ground up. Test flights in 2025 and 2026 have turned theory into evidence. Early prototypes struggled with heat shield durability, shedding hundreds of ceramic tiles during re-entry. By the seventh integrated flight test, tile loss rates had dropped by more than 80%, thanks to thicker interlocking tiles and robotic pin welding. Each new vehicle incorporated lessons from the last, with post-flight inspections guiding rapid improvements. The booster catch system, once dismissed as science fiction, has now been proven in action. In October 2024, Super Heavy was caught by the launch tower's mechanical arms for the first time, landing within 1 meter of its target. This system removes the need for ocean recovery, and it lets the booster be readied for another flight in days rather than weeks. Engineers monitor arm wear and grid fin alignment after each catch, aiming for 100 successful recoveries before major overhaul. Early catches required lengthy inspections, but by mid-2026, turnaround times have shrunk dramatically. On the ground, launch infrastructure is scaling up to match these technical gains. FAA filings indicate that SpaceX is preparing 3 active launch pads, with the potential for more than 100 flights per year. Each pad is equipped for rapid refurbishment, robotic tile replacement, and high-throughput propellant loading. These advances support a cadence that would have been unthinkable even a few years ago. With every successful catch, every reduction in tile loss, and every new pad brought online, Starship's promise of Current launch providers charge anywhere from $2,000 to over $10,000 per kilogram to reach low Earth orbit. Starship's business model aims to collapse those numbers to the low hundreds, and in time to less than $100 per kilogram. This isn't just a matter of engineering, it's a financial gamble built on relentless reuse and volume. Every booster that returns to the pad, every heat shield that survives another flight, helps spread the enormous development costs across a growing fleet of launches. The numbers only work if the flight rate climbs. Aerospace economists point out that the break-even point for Starship depends on flying dozens, if not hundreds, of missions each year. At full cadence, the marginal cost of each launch drops sharply, making ambitious goals like lunar landings or Mars cargo runs economically plausible. But if turnaround times, drag, or refurbishment costs spike, the price per kilogram could stay stubbornly high, eroding the promised savings. The financial engine powering this model is Starlink. Starship is the only vehicle capable of launching the large next-generation Starlink V2 satellites in bulk. Each successful Starlink deployment brings in new users and revenue, feeding back into Starship's development budget. This cycle, satellites funding rockets and rockets launching more satellites, creates a self-reinforcing loop. But it also means that any delay in Starlink V2 launches or a slowdown in user growth puts pressure on the entire Starship program. The economics of low-cost access to orbit hinge not just on technical achievements, but on maintaining a steady, rapid launch cadence and a healthy stream of satellite revenue. Orbital refueling sits at the heart of Starship's promise and its greatest gamble. The Artemis lunar landing, Mars missions, and the entire economic model for rapid, low-cost access to space all depend on a single unproven maneuver, transferring hundreds of tons of cryogenic propellant between two starships docked nose to tail in the vacuum of low Earth orbit. The physics are unforgiving. In microgravity, fluids do not behave as they do on Earth. Liquid oxygen and methane drift in blobs, clinging to tank walls, refusing to settle at the bottom. SpaceX engineers have turned to small thrusters to create gentle acceleration, called ullage burns, nudging the propellant into position for transfer. Even with this, the risk of slosh and gas ingestion remains. If bubbles enter the transfer lines, a pressure spike or pump cavitation could halt the operation or damage hardware. Chill down is another critical step. Before any transfer, the plumbing must be cooled to cryogenic temperatures below minus 180 degrees Celsius to prevent flash boiling and ice formation that could block valves. Specialized sensors track the temperature drop, while insulation and sun pointing attitudes help minimize heat leak and boil off. The transfer itself relies on pressure differentials, pushing propellant from one ship to another without pumps, using two separate lines for methane and oxygen to maintain balance. Each connection is a potential failure point. Valves must seal perfectly, and any leak could end the mission. The first full-scale demonstration is scheduled for 2026. If successful, it will prove that Starship can refuel itself in orbit, unlocking lunar and deep space missions. If it fails, the consequences ripple through NASA's Artemis program and SpaceX's own ambitions. Cryogenics experts warn that no amount of ground testing can fully replicate the fluid dynamics of zero gravity. The outcome of this single experiment will define the path forward, not just for Starship, but for the future of human spaceflight. NASA's lunar ambitions now rest on a single hardware solution. The Artemis III mission, scheduled for late 2026, cannot proceed without Starship's successful orbital refueling, a maneuver yet to be proven in space. NASA's Human Landing System contract named Starship as the only vehicle capable of delivering astronauts from lunar orbit to the Moon's surface and back. Any setback in SpaceX's timeline, whether from technical delays or regulatory holdups, instantly threatens the Artemis schedule. Program managers acknowledge the risk. A single missed milestone could push lunar landings back by years, with cost overruns measured in billions of dollars. Meanwhile, defense analysts track Starship's rapid launch and heavy lift capability for its potential to reshape national security. The Outer Space Treaty draws a legal boundary, but Starship's ability to deliver cargo or even military payloads anywhere on Earth within an hour has not gone unnoticed. Both NASA and the Pentagon face a reality where the success or failure of one commercial rocket ripples through America's space and security strategy. Competition for heavy lift dominance is heating up across the global stage. Blue Origin's New Glenn, with its 7 BE-4 engines and a projected 45-ton reusable payload, is targeting its first flight in 2026. China's Long March 9, designed for up to 150 tons to low Earth orbit, is aiming for a debut before the end of the decade. Rocket Lab's Neutron and ULA's Vulcan are scaling up, but neither matches Starship's size or cadence ambitions. Yet timelines slip and technical milestones remain unproven for every contender. SpaceX's long-term vision stretches far beyond Earth orbit. Starship was engineered with Mars in mind, the ability to refuel in orbit, carry large crews and cargo, and most importantly, produce propellant on the Martian surface using local resources. This concept is called in situ resource utilization, and it is essential for round-trip missions and the dream of a self-sustaining settlement. 4 milestones will define the next chapter. The first is the bulk Starlink V2 deployment by Starship. The second is a successful orbital propellant transfer. The third is a sustained launch cadence above 1 flight per week. The fourth is clear evidence of Mars-ready propellant production. These markers offer a real-time scoreboard for who leads the new space race and who has the tools to reach Mars first. Right now, Starship stands as the only launch system capable of fundamentally redrawing the map of space access. If SpaceX delivers on its vision, space will become an arena shaped by who moves fastest, not who spends most. The countdown to a truly new era has already begun.